All right, in this chapter, we are going to talk about um, carboxylic acids and amides. All right, so a carboxylic acid, all right, has a carboxyl group, and a carboxyl group is anything that you have a carbonyl with an OH attached to it. So this is the carboxylic acid group to it. Okay, the simplest carboxylic acid, well, actually not the simplest, but probably one of the most common is acetic acid. The simplest would have a hydrogen here. It's kind of like an aldehyde and a carboxylic acid, but it's technically a carboxylic acid. That would be the simplest, and that's called formic acid, right? And formic acid is the acid found in fire ants. So if you get bit by a fire ant, the burning sensation is the formic acid that you're experiencing. All right, these are abbreviated ways to write carboxylic acids. We've talked a little bit about this in class, either COOH or CO2H. Esters is another class of compounds that's what we call a carboxylic acid derivative because it comes from a carboxylic acid. And that's an ester where an ester has an R group in place of the H. All right, so that is basically what esters are. Abbreviated forms are COOR or CO2R. All right, and amides are another um, derivative of carboxylic acids where you have a nitrogen in place of an OH. And the R's in this case could be alkyl groups, so any kind of carbon-hydrogen group, or it could be hydrogens. So you could have an NH2 there. So something that looks like this with a carbonyl. And then you can have a nitrogen with either one hydrogen and an R group or two hydrogens and no R groups. Those are amides. All right, and amides are classified based on the number of carbons they have. Like I just said, you can have NH2s, which would be called a primary amide. If you have one carbon, I'm sorry, if you have the carbonyl plus an R group, it's called a secondary amide. And if you have all R groups, it is called a tertiary amide. Cyclical esters. So if you have an ester, so notice this is an ester because you have a carbonyl with an R group. See, technically that's an R group attached to my oxygen. They're called lactones. And cyclical amides are called lactams. Okay, so it's still an ester, but if it's in the cyclical form, we call them lactones. All right, and if it's a cyclical amide, it's called a lactam. All right. These groups are called acyl groups. That's just kind of a common name. An acyl group is any kind of carbonyl with a R group, and you can have pretty much anything attached to there, and it's considered an acyl group. Okay. As far as the geometry is 120 degrees. They're trigonal planar. Your bonds are polar with a more of a positive charge on your carbon, more of a negative charge on oxygen, because oxygen is more electronegative than your carbon. So your carbonyl is a relatively polar group because the electron-rich oxygen and the electron-poor carbon. This is identical to what we saw when we looked at ketones and aldehydes. All right, naming carboxylic acids. Basically all the same rules. You look for the longest chain that contains the carboxylic acid group. All right, the carboxylic acid group is always at the end of the chain. Okay, so it's always your carbon 1. So you don't have to tell the reader 1 carboxylic acid because it's always at carbon 1. It's always at the end of a chain. All right, and basically you end the parent name in oic acid. Okay, so if it's 5 carbons, it would be called pentanoic acid. That would be a 5-chained carboxylic acid. And then you apply all the normal other nomenclature rules. So here's an example. All right, our longest continued chain that includes the carboxylic acid would be this chain right here. You start counting from the carboxylic acid. That's always carbon 1, 2, 3, 4, 5, 6. So think about the name of this. Think about what the name would be in your head. So 4,5-dimethyl hexanoic acid. All right, so 4,5-dimethyl hexanoic acid. Pretty straightforward. You don't have to put the 1. You don't have to say hexane 1-oic acid because carbon 1 is always the carboxylic acid. Okay, here's some common carboxylic acids. Like I said, here's formic acid, which is environs. Acetic acid is vinegar, and benzoic acid is actually used as a preservative. Actually, if you add base to this and you pull off this acidic proton and for a negative charge there, it's actually called sodium benzoate, which is a food additive. Okay. The carbon adjacent to the carboxylic acid is called the alpha carbon. So this carbon right next to the carbonyl in a carboxylic acid, that should be an OH right there, is called the alpha, and this is called the beta carbon. Because if you have groups hanging off of here, rather than becoming like 2-hydroxy whatever, they call it alpha hydroxy. All right, we'll see that when we get to a different type of molecule later in this chapter. All right, esters, in naming esters, pretty straightforward. Okay, what you first do is you first name the group that's hanging off of your oxygen. That makes the ester group. Usually it's a very simple name. It's like an ethyl group, a methyl group, a terbutyl. All right, they're usually pretty straightforward, easy names, ethyl or methyl. So the way you can name this is you name this part first, then you name this part second, and you end it in O8 ester. Okay, so you take the ic acid and you put 8. Okay, so and this becomes the second part of the name. All right, so in this case, this is ethyl. Okay, now they are using a common name in calling it acetate, but you can also call uh, ethanoate. Okay, so ethyl ethanoate would be another name for this, but this is kind of a common name for it. Okay, so I'm not really going to hold you that responsible for naming esters really on the exam. I just kind of want you to kind of have an idea of that you first name this part of it first, then you usually name this followed by 8 at the end, or anoate, so ethanoate. All right, amides, you replace the oic acid with amide, pretty simple. So acetamide, that would be called acetamide, and this is benzamide. All right. Um, so let's just hear some examples. Okay, so I'm sorry. So in this case, notice we've got hydrogens here. Okay, so I don't have different R groups. So this is called acetamide. I don't have to worry about the hydrogens. But what happens if you do have an R group? So I have a secondary amine. Here I have a tertiary amine. I have methyl groups. Okay, well, you need to tell the reader what groups you have off of the nitrogen. It's kind of like the ester case. All right, in the ester case, you have to tell the reader what groups are hanging off of the oxygen. In this case, you have to tell them what's hanging off the nitrogen, and you show that by writing an N. So you do like capital N, and then you write the word ethyl, all right, and then a formamide in this case because it's a 1 carbon. Okay, in this case it'd be NN dimethyl benzamide. All right, so I'll kind of show you the names as we go through the slides, but you see that this N, you have to write this N first. So I have an ethyl group, so N-ethyl. This would be NN dimethyl. Okay, this group is a formamide. That's a formamide group. This is, since this comes from benzoic acid, oh, this is called benzamide. Okay, so this is called N-ethyl because the ethyl is attached onto the nitrogen, and then you name the formamide part. Okay, and then same thing over here. You've got NN dimethyl, and then you have the benzamide. Again, amides aren't really going to be asked of you to name on exam, but you should kind of have an idea of how to name them. Okay, hydrogen bonding, physical properties. You definitely have hydrogen bonding with carboxylic acids and with amides. Okay, carboxylic acids and amides. You have hydrogen bonding. Esters, you really do not have hydrogen bonding because you don't have a polarized hydrogen on there. But it is a relatively polar molecule because it can form hydrogen bonding if you have water in there. Carboxylic acids have the highest boiling points of all the functional groups, higher than alcohols, right? You can see that the alcohol is 97, but the corresponding acid has about a 20-degree higher in boiling point because you have more hydrogen bonding areas to it. Okay, esters have much lower because you don't have the hydrogen bonding. All right, primary and secondary amides have higher boiling points than tertiary amides and esters because you have the hydrogen available. So you have the hydrogen available on the hydrogen bond, but your tertiary amide does not have a hydrogen on here. So you can't really form hydrogen bonding. Okay, as well as in the ester, you don't have it either. Okay, just some interesting carboxylic acids. They are usually have a sour taste to them. I know they say a bitter odor, but they usually have sour taste. So think of a lemon. Lemons have citric acid in it. Okay, they also have ascorbic acid, which is vitamin C. And anything that's a fruit that's a, um, a citrus fruit has citric acid, which is sour tasting. So oranges, even though you want to consider oranges sour, they have a very small amount of citric acid, but you can sometimes eat a very sour orange. But like lemons and um, grapefruits, those really have quite a bit of citric acid and are relatively sour. Limes as well. Okay, so they usually have a sour taste to them. Formic acid, like I said, is the acid that's in fire ants. Vinegar is um, acetic acid. Also, if you ever have a bottle of wine and if you open it and you let it sit for a few days, it goes acidic. If you drink it after a few days, you kind of smell it or you taste it. That's also why when you go to a restaurant, they want you to taste the wine first just to make sure that it didn't go bad. Because what happens is the ethanol, all right, remember this is the structure of ethanol, has two carbons and an OH. In the presence of oxygen, oxygen is a very good oxidizing agent. It could oxidize that up to acetic acid. Okay, so anytime you have a sour or a vinegar taste or an acidic taste in any type of alcohol, that's because the ethanol has been exposed to oxygen for quite some time. Hexanoic acid is the smell in our BO. All right. Here they actually say it's in our dirty sock or like the locker room smell, or our BO is hexanoic acid. That's what our bodies are producing. Okay. Interesting skin products. A lot of times you'll see these alpha hydroxy acids. So remember I showed you that the carbon next door to the carboxylic acid is considered the alpha position. Well, this is called alpha hydroxy acid because the alpha position has a hydroxy group, which is an OH group, and then you have a carboxylic acid, so alpha hydroxy acid. This particular alpha hydroxy acid is called a glycolic acid. Okay, but this is a very special case, and here's lactic acid. If you exercise quite a bit, um, glucose is broken down very, very quickly. If you're exercising in a very, intense manner, um, and because you're exercising very quickly, the whole glucose molecule doesn't have enough time to actually break down. So you start using glucose. Okay, so what happens is glucose is 6 carbons, it breaks down into 3 carbons, and then the 3 carbons break down further and further and further. But the initial breakdown of glucose into 3 carbons breaks it down into lactic acid. Well, that could be done very, very quickly in the body and you get a lot of energy out of it. But once you form lactic acid and you break this down further, that process is much slower and takes a little bit more time and a little bit more energy. So if you are doing really intense exercising, your body says, well, I need energy now. I need it immediately and I need it quickly. So I'm going to break down as much glucose as I possibly can that's in our muscle. Well, what happens? You kind of get a burning sensation. Well, the burning sensation is the formation of lactic acid. You're forming lots and lots of acid, so you're increasing or you're decreasing the pH inside of the muscle, which in turn is creating a lot of acid, which acid has a burning kind of sensation to it. So when they say, oh, I'm exercising, I'm forming a lot of lactic acid, this is the actual chemistry of it, is that you have all this glucose in your muscle and it needs to break it down really quickly in order to get energy very quickly. All right, because once it forms lactic acid, that breakdown is much slower. All right, so Now you kind of know why, when they say I'm building up lactic acid, or even after if you exercise and then on the following day um, you're sore. That's actually a combination of things. One, it's a combination that you ripped a portion of your muscle. That's basically what you do when you weight train. You tear your muscle, all the microfibrils, and then they have to repair themselves. And when they repair themselves, they repair them larger and bigger and stronger because your body has to adapt to the stress on your body. So if you keep doing it, if you do it, you know, 3 times a week, you keep ripping your muscle, it has to build back. You rip your muscle, it builds back. You rip your muscle, it builds back. Every time it builds back just a little bigger and stronger every single time. Okay. And in the process, of you ripping down the muscle, it's using tons of energy, it's forming tons of that lactic acid, and that lactic acid stays around in your muscle for quite some time and kind of, in a way, quote unquote, it burns it because of the acid part. It's not really like burning it, but that's what it feels like, so that pain is still there. All right. So let's see, these acids by removing the outer older skin layers, really healthy looking. Okay, yeah, so these acids are also used in skincare, and because it is an acid, it basically removes the outer skin. I don't know if you ever heard of an acid peel, but an acid peel is something where they put a mixture of these compounds on your face, and they let it sit for a while, and then they clean it off. And what happens is the acid eats away at the very at the top layer of your skin, at the dead layer of the skin. All right. Um, and then here's some common acids that are used in anti-inflammatory and analgesics in everyday lives: aspirin and ibuprofen. You can see the carboxylic acid groups and naproxen. All right. Uh, Arachidonic acid is an acid that our body makes, which is a precursor to prostaglandins, which is inside of our body, um, which is kind of responsible as a pain response. So I'm sorry, it's a pain reliever inside of our bodies as of a pain response. So pain relievers work because they block the synthesis of prostaglandins, a compound that is responsible for uh, the pain response inside of our bodies. All right. So anytime that you hit your body or something like that, you start forming prostaglandins, and prostaglandins are actually responsible for the inflammation inside our bodies. Okay. And what aspirin does is it actually blocks the synthesis of prostaglandins. All right, so we're going to end this video right there, and when we come back, we'll start back at 17.5.